Hello, and welcome to FlippedHarber for Precalculus. In this video, we're going to take a look at section 1.4, Inequalities. Our objectives for this lesson are that we learn how to solve an inequality, solve a combined inequality, solve a quadratic inequality, solve a polynomial inequality, solve a rational inequality, and look at how to solve an inequality involving an absolute value. There's two types to those. Our topics are using properties of inequalities and then solving the various types of inequalities. Now, our properties for inequalities, I'm not really going to go over these in detail. These are in your book. I would write them down right now because these would make great notebook quiz questions. But a lot of these are really basic stuff. Like the trichotomy property says simply that a number is less than another number, or it's equal to, or it's greater than that other number. Those are the only three options. Numbers are either less than each other, equal to each other, or greater than each other. That's it. Here's some more properties. So let's look at how to solve a simple inequality. You've done this before. When you want to solve a simple inequality, it's just like solving an equation. We're going to add, we're going to subtract, we're going to multiply, divide. And that's basically it, just like you would if it was an equation. The only difference is that whenever you multiply or divide by a negative number, you have to remember to flip the inequality sign. You know that. Let's take a look at how to solve this simple inequality. 2x minus 2 is greater than or equal to 3 plus x. I'm going to add 2 to both sides, and now I'm going to subtract x. So I've got my x alone on one side with a number on the other side. X is greater than or equal to 5. My answer is boxed in just like it would appear on your homework. Now let's take a look at how to solve a combined inequality. A combined inequality has three parts: a left, a right, a middle. Normally it's set up so that the smallest number is on the left, then the middle, and then the biggest number is on the right. Again, we're going to solve this like we would a simple inequality or an equation. We're going to add or subtract, multiply or divide to remove numbers and get the variable alone. Specifically, we want that variable x in the middle. Now, the only thing to remember here is that whatever you do to one region, you have to make sure that you do it to all three regions. This isn't just a simple whatever you do on the left, you do on the right. Whatever you do on the left, you have to do on the middle and the right. So let's solve and graph this inequality. Now we're going to start out by simply subtracting 2 from all three spots. That gets rid of that 2 in the front, in the middle. Now I'm going to divide by a negative 2. Now remember, whenever you divide by a negative number, you need to flip those signs. So I get 5 halves is greater than or equal to x is greater than or equal to negative 7 halves. Now if this was your answer on your paper, you'd get it totally right. I'd give you all the points for this. But there's technically a better way to write it. We should put the smaller number on the left, the larger number on the right. But when we do this, again, those signs flip. So now it reads negative 7 halves is less than or equal to x is less than or equal to 5 halves. All this does is it puts the small number on the left, the big number on the right, which is the way math works. Small numbers are on the left of the number line, big numbers are on the right. So now let's graph this. We put a closed circle, because of the or equal to, at negative 7 halves and at 5 halves. We shade in between. Notice that I've put a box around the entire inequality solution and the number line. And that's how you should do it on your paper. There should be one big box around your whole answer, not a bunch of little boxes around different parts of the answer. Let's look at how to solve a quadratic inequality. Now, a quadratic inequality is simply an inequality that has an x squared. Just like a quadratic equation has an x squared, a quadratic inequality has an x squared. We're going to rewrite this as an equation. Now, you can technically kind of skip this step, but we do it because people are generally more comfortable with quadratic equations than quadratic inequalities. But we're going to rewrite it as an equation. We're going to solve that new quadratic equation, preferably by factoring. Now, these two solutions, because quadratic equations typically have two solutions, create regions on the number lines. We'll take a look at that actually using a number line to help organize our thoughts. We're going to pick a number from each of the regions created on the number line, and we're going to try those numbers in the inequality to see which ones work. So the solution to the inequalities are the regions that work. All right, that's a lot of stuff going on. Let's take a look at it. Here's our quadratic inequality. I changed it to an equation. I also moved that 12 over so that we are ready to factor. We go ahead and factor it. We've got the factor x plus 3 times x plus 4 equals 0. Now, we know how to solve this quadratic equation. We know how to solve this factor equation. That's why we wrote it as an equation. But honestly, you can do the exact same thing with the inequality. So let's go ahead and solve the equation. So we set the factors equal to 0. And we solve. So we have x equals negative 3 or x equals negative 4. Now again, this creates three regions on the number line. The region before negative 4, the region between negative 4 and negative 3, and the region after negative 3. Now, one or two of these regions are going to work. We have to figure out which regions work. The way we do that is we choose test numbers. One test number from each region, and we take those test numbers and we plug them into the inequality. So what should I choose for test numbers? Well, you always want to think logically about this. Let's look at the region on the far right. I can choose any number that's greater than negative 3. I can choose negative 2, negative 1, 0, 1, 2, 3. I can choose any number in between them. I could choose negative 1.54. Well, that would be kind of silly. The best choice in that region would be the number 0 because it's easy to plug in. Looking at the first region, I've got to choose a number that's less than negative 4. Don't get ridiculous and choose, negative 22. Keep it simple. We'll take negative 5. Now I have to choose a number between negative 4 and negative 3. Again, technically I could choose any number in that region I want. Negative 3.14, negative pi. No, keep it simple. How about negative 3.5? Now we're going to try each of these numbers, and I'm going to plug them into this last form of the inequality. Now, the reason for that is because this factored form of the inequality is actually pretty nice to work with because I have something is less than 0. Really, all I care about is whether it's positive or negative, because negative numbers are truly less than 0, positive numbers are greater. So whenever I get a positive number, it doesn't work. So let's try negative 5. If I plug negative 5 into the left side of that inequality, I get 2. Well, that doesn't work because 2 is not less than 0. If we plug in negative 3.5 into the left side of that inequality, we get negative 0.25. Negative number, less than 0, that works. Plugging in 0, nice easy number to plug in. Plug 0 into that left side of the inequality, I get 12, less than 0. No, doesn't work. So the only region that worked was that middle region. So my solution is an inequality that represents the region that works. So my solution is the inequality negative 4 is less than x is less than negative 3. Now, you might be sitting there wondering, hey, whoa, how do we know that it's not negative 4 is less than or equal to x? Well, to answer that, look back up at your original inequality. If your original inequality does not include the or equal to, your solution shouldn't. So since I don't have the or equal to in my original inequality, my solution does not have the or equal to. Now, solving a polynomial inequality, pretty much the exact same way, except we can have more factors. More factors creates more regions. We're going to pick a test number from each region. Some of the regions will work, some of the regions won't. Don't start writing your answer until you've checked every single region. Now, sometimes they give you a complicated looking polynomial like we see here, x plus 2 times the quantity x squared minus x plus 1. Sometimes they'll give it to you totally factored out. When they give it to you factored out, don't ever multiply it together. Don't ever do it. You want it factored out. Don't multiply. So, let's take a look at this inequality. First thing I want to do is change it to an equation. It just makes people more happy that it's an equation rather than an inequality. Now, I've got two factors. I set each of those factors equal to 0. Now, x plus 2 equals 0, simple. X squared minus x plus 1 equals 0. Well, it's a quadratic equation. I should try to solve it by factoring. If I can't, then I have to try something else. And by the way, x squared minus x plus 1 does not factor. Well, what do we do with the quadratic equation that doesn't factor? Well, we bring in our old buddy, the quadratic formula. So we get x equals negative 2 from our first little equation. And then from the quadratic formula, we get x equals 1 plus or minus the square root of 1 minus 4 all over 2. Okay, remember the quadratic formula, x equals negative b plus or minus the square root b squared minus 4ac all over 2a. You should know that by now. Look at the discriminant. The discriminant is the stuff under the square root. That's a negative number. 1 minus 4 is negative 3. There's no real solutions from this, so we get to totally ignore it. So we only have x equals 2 to deal with. We get two regions, all the numbers before negative 2, all the numbers after negative 2. I'm going to choose the test numbers negative 3 and 0. 0 is always a good one to try. I'm going to plug them into the original inequality and see which one is greater than 0, which one's less than 0. Maybe they'll both work. I doubt it. Maybe they both won't work. I doubt it. What I'm expecting is that one region works and one region doesn't. But I'm not going to start writing my solution until I try both. So I plug in negative 3, and I get negative 13 is greater than 0. Well, that's not true. That whole region doesn't work. I plug in 0, I get 2 is greater than 0. Yeah, that does work. So the region to the left of negative 2 doesn't work. The entire region to the right of negative 2 works. So my solution is that x is greater than negative 2. Now let's take a look at another polynomial inequality. In this one, they give us our polynomial as 3 factors all multiplied together. Do not multiply them together. Leave them just like this. Set that sucker equal to 0. Now take each factor and set it equal to 0. So I get x minus 1 equals 0, or x minus 2 equals 0, or x minus 3 equals 0. Solve each of those. X equals 1, or x equals 2, or x equals 3. Great. I've got 3 numbers to mark on my number line. That creates 4 regions. I need to test the numbers before 1, the numbers between 1 and 2, the numbers between 2 and 3, and the numbers after 3. So I'm going to choose 0, 1.5, 2.5, and 4 for my test numbers. Now, just about anything is possible here. Maybe the first region works, the second region doesn't, the third region does, the fourth region doesn't. Maybe it alternates like that. Maybe the first two work and the second two don't. We don't know until we test them. So, we plug in 0, we get -6 is less than 0. That's true. We get a negative number that's less than 0. That works. We plug in 1.5. Is that less than 0? Yes, it is, because it's a positive times a negative times a positive. It doesn't matter what the number actually is. I know it will be negative, so it's less than 0, so it works. Taking 2.5, I get 1.5 times 0.5 times -0.5. I don't care what that is. I just know that that's going to be negative. So it works because the negative number is less than 0. Taking 4 and plugging it in, I get 3 times 2 times 1. That's not less than 0. That's a positive number. So that last region does not work. Now, our first region, our second region, and our third region all worked. That means that all the numbers less than 3 work. And that's actually my solution. X is less than 3. Don't start writing your inequalities until you've tested all of your regions. Let's take a look at solving a rational inequality. What we want to do is we want to start by factoring the top and bottom of the ratio. Now, this rational expression, x plus 1 over 1 minus x, is less than 0. It's already factored. X plus 1 is our factor on top, 1 minus x is our factor on bottom. Not a whole lot of work to do there. We set our top factors equal to 0. We technically set our bottom factors to not equal 0 because we can't have those bottom factors equaling 0, because that would break a very important rule that we can't have 0 on the bottom of a fraction. Now, these values that we get create regions just like we saw in the polynomial and quadratic. We're going to deal with this a slightly different way. We're still looking for regions that work and regions that don't work, but we're going to organize it a little bit different. So we set our top factor equal to 0. We set our bottom factor to not equal 0. If you set it equal to 0, I don't care. It's just to get the numbers. We get x equals -1 for the top factor equaling 0, and we get the fact that x cannot equal 1. If we plugged in 1, we would get 0 on the bottom of the fraction. We can't have that. Again, we mark these numbers on our number line, and we create regions. All the numbers before -1, the numbers between -1 and 1, the numbers after 1. Now, this graphic here, what I've done is I've marked the regions based on whether the top is positive or negative and whether the bottom is positive or negative. So the top, x plus 1, is negative in the first region. If you plug in a number like -4, -4 plus 1 is negative. So that whole region is negative. The middle section, from -1 to 1, x plus 1 is positive. If you go 0 plus 1, that's a positive number. If you choose a number from the third region and plug it in, you get a positive number again. Let's do something similar with the bottom factor. 1 minus x, if you plug in a -4 into 1 minus x, you're going to get a positive number. So that whole region is positive. If you choose 0 and plug it in, you're also going to get a positive number. If you choose a number from the third region, like 3, 1 minus 3, that's a negative number. So now we have to ask ourselves, well, what if we go ahead and divide these? In the first region, if you take a negative, divide it by a positive, you get a negative. In the middle region, you take a positive, divide it by a positive, you get a positive. In the third region, you take a positive, divide it by a negative, you get a negative. So we're interested in where this rational expression is negative, because we're interested in x plus 1 over 1 minus x is less than 0. So that means we're interested in where it's negative. It's negative in the first region and in the second region. So that first region is where x is less than negative 1. The second region we're not interested in. The third region is where x is greater than 1. So that's our solution. X is less than negative 1 or x is greater than 1. All right, here's some theorems that we're going to use when solving absolute value inequalities. The thing to start with is if a is any positive number. Okay, a is a positive number. A is not 0, a is not negative. If a is a positive number, then this theorem helps us to set up our solutions for absolute value inequalities. I'll give you a second to write these down. Alright, so when we want to solve inequalities involving absolute values, we use the appropriate part of the theorem to rewrite the inequality. So we use those things from the previous screen to rewrite the inequality. And then we solve it like any other inequality, because that absolute value is going to go away. So let's take a look at this inequality that involves an absolute value. The absolute value of x plus 4 is less than 2. We go to our theorem and we look at which one this looks the most like. And what it looks the most like is the absolute value of u is less than a. Now the theorem says that we should rewrite that as a combined inequality. So that's what we're going to do with the absolute value of x plus 4 is less than 2. We're going to rewrite it as negative 2 is less than x plus 4 is less than 2. We strip off our inequality and we put that stuff in between a negative and a positive a. Well, now we can solve this. And we can solve it really simply by just subtracting 4 from all three spots. So we get negative 6 is less than x is less than negative 2. Here's another inequality. This time our absolute value is greater than or equal to 2. So we go back to those theorems, there's 4 of them, and we pick the one that this looks the most like. So we're going to rewrite this as two separate inequalities. One where the stuff inside the absolute value is less than negative 2, and one where the stuff inside the absolute value is greater than 2. Now I have two little tiny inequalities to solve. I'm going to solve them the exact same way. I'm going to add 3 to get rid of it. So I get x is less than 1, x is less than or equal to 1, or x is greater than or equal to 5. That's my solution. Alright, we've covered a whole lot here. A lot of it's pretty complicated stuff. A lot of it is very time consuming, even if it's not difficult. But you should know what your homework is. Remember to get started on this before class. You're probably not going to get through this if you wait till class to get it started. So get started on it now and have your questions ready to go when I see you in class. I hope you've enjoyed this, and I'll see you in class and I'll see you online.